There we are. Okay, so there's Liberty ships in the harbor. They're breaking apart in the harbor, even though they've been out at on the high seas and never had a problem. Then suddenly they're just sitting in the harbor doing nothing, and they break completely in half. So there was a bunch of study that was undertaken to try to figure out exactly what happened. You better be looking up Liberty ships on the internet.
That's exactly what we have pulled up.
All right. Apparently, I'm too boring. It's much more fun to read Wikipedia.
We're trying to find the answer for you.
It sounds like the welding may have made some stress concentration.
You haven't read through all the whole thing yet? We're not there yet. So what happened was the welding indeed did change the material structure. And that material behaved in a way that was what we're going to talk about today. So, yes?
Just a question about this. It seems odd that it would go up in the middle and not down in the middle. I feel like the middle would have more mass.
It's in half, man.
So like
up
it
to the middle,
broke
down
like
to the middle.
This. It just went like.
Right, so even if it broke from the top down or from the bottom up, it doesn't matter. It broke in half, and then the only thing left is the keel. The keel was still.
Oh, okay, okay. I was thinking like it was like a full breakthrough. I wonder why I didn't just. I feel like it would be more like it go down.
No, the keel is still holding it together. Anyway, so we're going to talk. So the fracture mechanics. This was a big, sort of a big funding. So you guys are too young. We have a guest. So at least one of us remembers the Challenger disaster, right? So the Challenger disaster. You guys know what I'm talking about? The Challenger disaster, you know, Kristen McAuliffe and all. So that funded a lot of research into trying to figure out what happened in the Challenger. So it was all kinds of money that was spent by NASA in funding different research efforts to try to understand what had happened. The same kind of thing happened with the Liberty ships. Liberty ships start falling apart in the harbor. We got to figure out what's going on. So there's a lot of study of fracture mechanics that resulted. Okay. So before I get back to answering how that happened, we're going to talk about the way that fracture mechanics is empirically studied in the lab. So the first thing, the first sort of characteristic mechanism we have for studying fracture mechanics is a Sharpie impact energy. Sharpie? Sharpie impact energy is a mechanism for characterizing the fracture behavior of a material. So Sharpie impact energy takes a specimen of a very specific geometry.
Specific to the material or
Specific to the Sharpie impact test. So there's the specimen. It is 10 millimeters square, so it's just a little one square centimeter and a bar, and 55 millimeters long. And then there's a V-notch cut in the top. And you can see the distinction there. It's a 45-degree included angle and a raise of curvature of 0.25 millimeters. So it's a very specific geometrical arrangement for this sample. Okay. So it's kind of like the modulus of rupture bars that we talked about, right? The long, skinny bars. But in this case, they add the extra V-notch because they want to make sure that this thing's going to experience its concentrated stress at that location. They want to control where the stress is located. Okay. And then what they do is they put it in this system. So you can kind of see here. Down here in the bottom right is the Sharpie impact specimen, right? And they put it in there with the V-notch pointing away, and then they have this really big hammer, big heavy hammer that's on a pivot. And the hammer has at its center point a knife edge, kind of a wedge there. You see that wedge on the bottom right? That's the point of that hammer. So the hammer will be dropped from a known height so that you can see on the top part there's a scale with the pointer. Ever see the pointer? So the pointer, you raise it up and it's telling you what the height of the hammer is. And then you let it go from that height and it comes down and whack! It breaks the Sharpie impact specimen and then goes up on the other side. And then there's typically some kind of a little push indicator that maps its travel up, and then it comes back down. And so you can measure, knowing here's the energy it had to begin with, right? The potential energy of the hammer. And then when it swings through, it comes to a lower height and you can measure the potential energy it had at the end. The difference between the two is the energy that was absorbed in breaking this material. The Sharpie impact energy. Okay? So the idea is to figure out how much energy it takes to break the thing, and then correlate that energy to the toughness of the material. Remember I talked about toughness. What was toughness? How do we measure toughness? Area under the stress strain curve. So we have the stress strain curve. Well, I'll do it in engineering stress and strain. Or look something like this. All right, and toughness is the area under that curve. Now, what did I say about brittle materials? How do they behave on this graph? All right, so the brittle materials, right, are high elastic constant, like that. Right, it takes a lot more stress to break a brittle material, but it breaks very quickly. So what's the toughness of a brittle material as compared to a ductile material? Right, very small. Right, the brittle material has very small toughness, the ductile material large toughness. And so we can map the Sharpie impact energy as a function of temperature in this case. And we can see that what happens is materials, just take one of these as an example. Right, it has a very high Sharpie impact energy at a high temperature. But there's this well-defined temperature, 25 degrees C for this particular material, where the impact energy dramatically drops off. What that means is, above 25 degrees C, that material is very ductile, has a very large impact energy, has a high toughness. But below 25 degrees C, it has a very small impact energy and behaves brittly. You have a question?
Yes. Does that,
Why is your hand down above you? There you go.
does that have to do with the, like, I remember a couple weeks ago you drew in a graph and there was like that like semi-fluid-ish
Right,
state.
so that is not what we're talking about here. It has nothing to do with that. Okay? What we have here is what's called a brittle to ductile transition temperature. So there's a temperature, and for that particular material is 25 degrees C, below which that material behaves brittly. But above it, it behaves ductily.
So does that exist for most solids?
So this is especially true, it does not exist for most solids. This is especially true for BCC low carbon steel. Okay, it's particularly true, it's not the only thing that happens in it, but it's especially true for BCC low carbon steel, which, it turns out, is what they made Liberty ships of. I brought that around? That's nice. So the Liberty ship behavior would probably be more like something, down in here, right? More like this. So the issue with the Liberty ships was they worked fine when they're out on the ocean, right? Out sailing the South Pacific, whatever, no problem. The problem occurred when they were docked in the Pacific or in the Atlantic North Atlantic, Boston, that kind of area. Because then the water's really cold, right? The water, in fact, during the wintertime gets below zero, right? Below 0 Fahrenheit, below 0 Celsius, right? Because it's salt water. And so the Liberty ships had a ductile to brittle transition temperature along these welded joints. Because again, I guess we haven't really talked about heat treating much, but what happens is when you weld them, you heat them up and they actually change the properties of the material. Right? To weld something, you have to melt some metal. And so you get really hot, and what happened was that section in there that used to be made of a different kind of material, now all of a sudden it's made of this low carbon BCC because it's been heated and allowed to cool and change structure. So now the welds are made, or the weld regions made out of this low carbon BCC steel, which experiences a brittle to ductile transition temperature that's in the neighborhood of where the cold water was. And so it was this brittle ship that literally just cracked in half. Just, I mean, it took very little, it took just the weight of the ship and the force of the waves lapping on the side to cause it to break. Yeah.
So not every material has a
Right.
brittle structural resistance.
You would not see aluminum doing this, following this behavior. Okay? It's something specific to certain particular narrow range of materials. Okay. So the Sharpie impact test, or Sharpie impact energy test, is 1 mechanism. Okay? For characterizing it. Now last time, or not last time, but previously on NCIS,
Great show.
okay. We talked about elastic cracks, right? Crack is the stress concentration in elastic cracks. Remember, sigma max equals, anybody remember? Anybody?
2 sigma
sigma.
C
C
over
over rho square root.
Okay.
Right, as we talked about last time. I'm actually going to use A now instead of C for the cracks, because I realized today that your book uses A for the crack length instead of C. It may have used C earlier, but in the fraction mechanics chapter, it uses A. So, did it use C? Did anybody look that up before? It was C before and now it's A? Yeah, that's great. Let's just mess with people's minds.
Oh, don't worry, that's what the 8th edition is for.
Yeah, straighten that up, yeah. There's also, if you look on, well, we aren't there yet, but if you look at the, on page 233, they replaced a P, pi with a P, so there are some typos in here. Anyway, okay, so we had that expression. All right, what was sigma?
Stress.
What stress?
Actual real.
Okay, so that's the,
Applied.
I'll call that, you're right, it's the applied stress, the macro stress. Right, that's the stress that's applied to the overall sample. Sigma max is the stress at the crack tip. Right? And then, as you said, C/A is the crack length. And then rho is the radius of curvature of the crack. So if I have a crack that looks something like this, if I fit maybe an ellipse, actually typically use an ellipse of which a circle is 1. Right? A circle is an ellipse with concentric foci. So the radius would in this case be the major radius. Right, it's the that horizontal radius. Okay, so that we already talked about. It turns out that in brittle cracks, that is cracks that where the material behaves elastically, right? Oh, I erased it. Nice. Draw it back up. Right, so the brittle crack, we're essentially in the elastic regime. Right, there's not really a lot of plasticity. Versus the ductile crack, which is going to have to operate where there's significant plasticity. Right, so in a brittle crack, where you're cracking the thing in an elastic regime, the stress needed to cause crack growth, needed to make that crack grow. So the stress, this stress, would be essentially the max stress when the crack starts to grow, right? When this is the stress that's caused by the external applied load. This is going to be the stress needed to make the crack grow. Understand the distinction? This is the applied, and this is the critical. So when the applied equals the critical, the crack grows. Does that make sense? Okay. So this is the square root. This is not in your book, I don't think. I couldn't find it. 2 gamma E over pi A. Where gamma is the surface energy. E is the elastic modulus, and A is the crack height. So gamma here is the only thing that's new. So basically what we're having to do in a brittle material, we have to put in enough stress to create new surfaces. Right? For that crack to grow, I have to break those bonds, create new surface. And there's an energy associated with that, with having a surface, because it doesn't want to be a surface, right? It wants to be, made into itself. So the surface energy is on the order of 10 to the second to 10 to the fourth for most metals. It'd be, for like a polymer, it'd be less than 100, so it'd be below that range for something like plastic. Okay, that's why it's easier to crack a plastic than it is to crack a metal, even a brittle metal.
So, is that the same energy that you factor the sharp impact test?
So that is not the same energy. No, no. This is sort of the microscopic atomic scale surface energy. Right.
So, okay, so then how does that signal apply to the signals above?
So what I'm saying is, as soon as your applied stress is equal to or greater than the surface energy necessary to create fracture, the crack will propagate. You'll break it in half. All right, so I have a crack, a pre-existing crack in a material. That pre-existing crack will concentrate the applied stress to a larger value. As soon as that concentrated value exceeds that necessary to cause the crack to propagate, basically as soon as that stress is big enough to break the bonds that you have out here, that will propagate through the material.
So as soon as sigma max equals square root of 2.
Right. So as soon as these two things are equal, then we'll get crack propagation in an elastic material, in a brittle material. Yes?
If you maintain your applied stress, then that crack should go all the way through the material.
Right.
Because your length is increasing.
Because A is getting bigger. Right, so as A gets bigger, this number, the necessary stress gets smaller, and the applied stress gets bigger, so it just becomes worse on both ends. So that's why it's very difficult to control, to take a piece of glass and get the crack to grow partway through it. Right? If I have a crack in the glass, I pull on it, boom, it pops all the way through. Right? It's catastrophic. Right? Glass doesn't generally fail in little bits and pieces. Now, in your windshield it does, because remember we talked about the fact there's another layer there gluing together, so it's getting support. But if I take, this window, once the crack goes, it goes everywhere.
You test that sometimes.
No. Okay, so that's for an elastic crack. For a plastic crack, for a ductile crack, in ductile cracks, we have a similar kind of relationship. Square root of 2, I'm sorry, not 2. I don't think that, yeah, we just brought that out. E times gamma plus P over A. Where P now is the plastic strain energy.
It's not the elastic modulus.
E is the elastic modulus, P is the plastic strain energy. Okay, so in other words, it's the energy necessary to cause plastic deformation. It's the energy necessary to propagate dislocations. Right, Burgers vector squared, it's proportional to Burgers vector squared, that kind of thing. You remember what I'm talking about? And P, it turns out, is on the order of 1,000 times gamma. It takes a lot more energy to propagate deformation, dislocations and such than it does to create new surface. That's why this stress is much higher. It takes a lot more stress to cause a crack in ductile material than it does in a brittle material. Because in a brittle material, all you have to overcome is the surface energy. In a ductile material, you have to overcome the surface energy, plus you've got to cause the deformation. And that's why there's a much higher energy absorbed, because you can turn the energy into stress distributed through a distance, stress acting through a distance. There's a much higher energy and therefore much higher stress involved in ductile fracture than there is in brittle fracture.
So what is P again?
P is the plastic strain energy, the energy necessary to cause all that plastic deformation. Okay. Okay. So let's go with that. Yeah. Okay. So is everybody okay on those concepts? So let's look at one other thing related to fracture. And that is fracture toughness. So fracture toughness is different than just regular toughness. Fracture toughness is is its own thing. It's a material property, first of all. So that if I said I have 1% manganese, low carbon steel, it would have a particular fracture toughness. Just like an elastic modulus or tensile strength or yield strength, it's a property of a particular material. It accounts for, because it's a property of a particular material, it accounts for the structure. In other words, if I change the structure of the material, so I might not change the chemical composition, but I might change the grain size. I don't know why it has such a problem with me. Dr. Denning never has this problem. I think it's actually, I think my flashcard.
I know, I don't even know how
card. But anyway, K1C. So it's the 1 here, the Roman numeral 1, corresponds to loading it in this configuration. There's also a tearing mode and a shearing mode. There's 3 different modes of crack propagation. Right? I could take this and shear it like this as well. That would be a different mode. Or I could tear it like this. And that would be a different mode. And each of those has a different way of, different constraint. But in this case, this is sort of the most generic mode 1 loading. And it's defined as y times sigma f times the square root of pi times a. So y is a parameter it's sort of an empirical parameter. It's on the order of 1. Sigma sub f is the macro stress at failure. So in other words, that's the sigma that's applied out here. When you applied to the sample. And then again, A is, as it was before, crack length. So what does that mean? That is a fixed parameter for a material. So as I increase the applied stress, right, I have to decrease the A in order to get, to maintain the system. So if I have small cracks in the surface, it'll tolerate a larger stress before it fails. If I have large cracks, it will only tolerate small stress before it fails. Does that make sense? Okay, yes.
And y is basically 1.
Why is it in there? Because they have to, it's not exactly 1, so it's an empirical parameter. Because not everything behaves exactly according to sigma times square root of pi a.
So it just depends on the material.
So for each material, they're going to be they're going to vary the y, or for each particular set of environmental conditions or whatever. So y is going to vary, but it's not. For most of the things we would do, we would just assume y equals 1. Okay. So what does that mean? That means if I were to plot now the stress at which something fails, if I were to plot the stress as a function of, actually it's usually plotted on a log plot, and I plot the failure stress, it will follow this kind of a behavior. Right, this is sigma equals K1C over the square root of pi a. Or if you want to do it sort of K1C over the square root of pi, which is a constant, times 1 over the square root of a. So essentially it's a 1 over square root of a dependence. So if I have very large cracks, the stress at which it fails is going to be small. If I have smaller cracks, it's going to be larger. And eventually, this curve comes across at the yield point. And so at some point, the cracks are small enough and the fracture toughness large enough that those small cracks aren't enough to cause enough stress concentration. And I just get general yield out of the material. So it's only when cracks are bigger than this critical size only when the cracks are bigger than that critical size will the crack length actually have an impact on the strength of the material. Anything smaller than that, doesn't matter that the cracks are there, because they don't concentrate the stress well. Okay? So, if you have something that has a low KIC, a K1C, if you have a low fracture toughness, a small fracture toughness, that means it takes a small stress for a given crack length to break it, which means it's brittle. If I have a large fracture toughness, then it requires a large stress to break it, and so it's ductile. So effectively, what we're doing here, we're not actually quantitatively doing it, but the impact energy in the Sharpie test is measuring roughly, at least qualitatively, the fracture toughness. Here we have a high fracture toughness, here we have a low fracture toughness. Ductile, brittle. With me, without me. All right. Anybody got it? Well, what is it, night and day?
I thought you were just like chuckling.
No,
You actually.
my mom loves that movie.
Just
It's
like-
one of her favorite movies.
I was like, he
of all
doesn't
time.
really know. He's just sucking up.
He's just not.
No.
With me?
His mom loves that movie though.
With me?
I'm-
You guys know it, bro?
No.
No? Night and day?
I think you gotta close that book.
All right.
No, I said I did that.
So,
But-
Roadhouse. No. Tom Cruise and,
Show me the money.
What?
Cameron Diaz.
Show me the energy.
what's her name?
Cameron Diaz, isn't it?
Cameron Diaz, yeah, sorry.
Fine.
Yeah, no, just answered it, yeah.
Mariah Carey, Cameron Diaz. All right. Anyway, okay, so what do we do? So what do we do when we're out here? Right? What do we do if we've got a defect? Right? We want to toughen the material. We got to do something to blunt this off, right? Right. So what we can do is one of two things. One I've already talked to you about.
Increase the radius.
Increase the crack to radius. So how can we toughen it? So we can toughening. There's two major mechanisms for toughening. One is crack tip blunting. So we can drill a hole at the end of the crack. Right? Has anybody else gone home since we last discussed this and tried the potato chip bag experiment? You see it? Did you try it?
You necessarily
I actually got a better way of opening bags now because of it.
Okay, so there you go. See? My job here is done. All right, so crack tip blunting, drilling a hole at the end of the crack, rounding off the crack so that it's not a, and that would, by the way, be a mode 2 crack, the tearing. Or that's mode I can't remember. It's been too long. It's either mode 2 or mode 3, I can't remember which is which. Anyway, but that's, you see how that's a different kind of a crack, right, than just pulling it apart, the tearing.
Are we gonna need to know the different kind of modes?
Crack tip blunting, what's that?
Are we gonna need to know the different kind
No.
of modes? Okay.
No. So crack tip blunting. Crack tip blunting doesn't necessarily mean drilling a hole though. I think as I was looking at the thing just now, I saw a picture. Yeah,
Is that how you
that's,
polish it?
yeah, shoot. That's not what I wanted. And I thought that was gonna be it. There's a
Microcrack.
cast iron. Depending on how you make your cast iron, you can make it more or less tough by changing the shape of, because cast iron, we'll talk about this later, but cast iron actually has little bits of ceramic embedded in it. And you can actually change the behavior of the cast iron by changing the shape of those little ceramic bits that are embedded. Because if you have, like that picture there shows cracks in the material, or yeah, little micro cracks in the material. They're kind of randomly oriented micro cracks. Like this. And then obviously the size here is exaggerated, but you get the general idea, right? So you have all these micro cracks in the material. You'd think that'd be a bad thing. But the nice thing about the micro cracks is when a big crack starts to propagate, it eventually encounters one of these micro cracks, and when it opens it up, I've just increased the crack tip radius of curvature hugely. I've blunted the crack. So these materials are typically fairly tough, considering what they are, because the cracks can't propagate as sharp cracks all the way across. They hit something and suddenly they're no longer a sharp crack. Stress concentration goes way down. So that's one way to toughen the material, is to put these extra, yes?
But those micro cracks, if they're shaped like that,
Yeah, but these micro cracks are much shorter length than this. So if the A is short, oh, I've erased it. Wherever the sigma, I can't even see it in the white erasure mess. Anyway, the sigma max equals 2 sigma square root of A over rho, right? Those have very small A's, so they have very small stress concentrations. Okay, they're small A's, they're down in here. We don't care about those. It's the big ones we want to blunt off. Does that make sense? Okay, so that's one way, blunting. And the second way that we can toughen of toughing is transformation toughening. Transformation toughening is where we take that same material and if you make it out of like zirconium oxide is the transformation toughened ceramic. So it's a ceramic material, and so it has high modulus and high strength, but it's brittle. And it's normally tetragonal. That's its normal state. But when you stress it, very much like tin, remember we talked about twinning in tin, when you stress it, it accommodates the stress, it deforms, not by creating twins, but by actually changing its crystal structure completely. So it goes, under presence of stress, it actually becomes monoclinic. So it actually changes crystal structure when it's stressed above a certain value. But the monoclinic form has a lower density. The packing of the atoms is not as tight in monoclinic as it is in tetragonal. Since it has a lower density, what happens is when it gets to that point, this region out here at the tip that experiences that stress suddenly decreases its density and therefore increases its volume. And the only way for that red region to increase its volume is for it to essentially close off the crack. It has to expand into the crack in order to increase its volume. So what it effectively does is it compresses the crack tip locally when it undergoes that transformation. So zirconium oxide, zirconia, is a transformation toughened material. As a crack begins to propagate in it, the stress created by this transformation stops it. Now, you can still get it to crack, but you have to apply the additional stress to now pull that monoclinic material apart. Okay. So it's tougher, but it's not infinitely tough. Does that make sense? Any questions? So this is like a whole course. Fracture mechanics is a whole course covered in one day. So that's why we, like I said, material science kind of a flyover kind of view of everything. And actually, typically, fracture mechanics is more likely to be even taught in the mechanics department than it is in material science, but nonetheless. Okay, does anybody have any questions?
What's the answer to the universe?
42. So we have 12 minutes. We can, and I forgot to bring in the answers, so we'll somebody got their calculator. The answers are sitting on the printer in the other room. But he's going to you're gonna fall on to Austin. Let the juniors handle. Let the juniors handle. Okay. All right. So a couple problems. Estimate the flaw size responsible for the failure of a turbine rotor made from partially stabilized zirconia that fractures at a stress level of 300 megapascal. So we have a turbine rotor. You know what a turbine rotor is?
Like a windmill kind of thing?
They're inside a turbine, for those of you who we were just talking about this in
Yeah.
thermodynamics.
So Q
They're the
dot
little-
zero.
You got a zero in this?
What's that?
So it's Q dot zero in this case?
So, turbine rotors are basically the little fan blades that that turn the pressure into the flowing fluid into rotational motion. Okay. And they use ceramics in the turbines because they can work at very high temperatures, which, as we'll see in thermodynamics, is advantageous from a standpoint of efficiency. Okay. So when we run something at high temperatures, we got to have a ceramic material because it works at really high, has high strength at high material or high temperature. But the problem is it's brittle. So this particular turbine rotor, this is the fan blade basically on the turbine, has broken because it's fractured at a stress of 300 megapascal. So we know that the failure strength is 300 megapascal. And they've asked us to determine the flaw size responsible for that failure.
So basically just like the crack length?
The crack length, yes, the crack length, that's what they're asking.
Okay.
So, what are we going to do?
Well, we always find out something about zirconia.
Find out something about zirconia.
I don't know what, so we're saying something about it.
Okay, what are we going to find out about it?
The K value.
The KIC value? K1C value? Okay, so what's the K1C value for partially stabilized zirconia?
9
9 what?
megapascal square root meters.
K1C is 9 megapascal square root meters. Right, because the expression for K1C, now I've erased it too. K1C equals Y sigma square root of pi A. So Y is the universe parameter, this is in megapascals, and A is in meters. Right? So if we see that it fails at 300 megapascal, then we should be able to identify A. How am I going to solve for it?
Stress squared divided by pi.
So just solve that for A, right? So K1C, which is tabulated value, divided by Y sigma squared times pi equals A.
Divided by
Divided by pi. Right. Divided by pi. Or I just put pi squared in there. No, pi, no, square root of pi. Whatever. You know what I mean. Yes?
Is there any sort of physical, what is a square root meter?
It's just
It's
in
just
units,
simply in
yeah, because they find that it's inversely related to, or it's related to the square root of the crack length. There's a 1 over root A dependency, right? So if I plot out sigma, the failure stress, like I showed on that other graph, it's also erased. There's a 1 over root A kind of dependency. That's all there. It's an empirically derived understanding, but it's a consistent value. That's why this is a material parameter. Right? For a given material, it will always behave in this fashion. Okay, so what's K1C? That's 9. And we'll just do everything in megapascal. Divided by Y,
1,
right? We just divide by 1 times sigma,
300.
300 squared divided by pi. So that's 9 over 300, which is 3 over 100, which is 0.03 squared divided by pi. Anybody got that?
I'm getting
286 microns. Is that what you're saying? 286 times 10 to the minus 6?
Yeah.
Okay. So 286 microns. Does that seem like a reasonable value?
Yeah, sure.
Yeah.
How big is 286 microns?
Actually, it's big.
pretty big compared to the radius of the atom.
It's right. It's very big compared to the radius of an atom, but we're talking about the crack length, not the crack radius.
Oh.
And
Right.
the tiny crack.
So the crack length, what's that?
That's a noticeable crack.
It's 3 hairs. Past a freckle.
3 hairs
Um,
thick.
You guys ever heard that? 3 hairs past a
About
freckle?
half a mole.
Okay. It's 3 hairs, right? So I mean, the average diameter of a hair is sort of between 80 and 100 microns. So it's 3 human hairs. So, yeah.
Oh, my
For a
God.
frog?
Yeah, all right. I'll add it. I mean, genie, but I'm just calling out the reference. Okay, so is that such a reasonable value? What? I'm gonna make you two sit in the front row. Actually, I'm gonna make you turning around so I can see what you're doing. All right, let's try the other one then. Let's go the other direction. Calculate the breaking stress for a rod of ABS. Know what ABS is?
It's a plastic, it's like a big plastic, right?
Right, it's a plastic. 3D printing is one of the places.
Automatic braking
They make plastic from it. No, it's not an automatic braking system.
Automatic
It
braking
is a
system.
pipe, the black ABS pipe, for instance, you see, anyway, it's a rigid plastic with a surface flaw size of 100 microns. So now we have a surface flaw, surface crack that's only 100 microns long. All right, so how are we going to calculate the breaking stress? What are we going to do?
Reverse the system.
Reverse the
So
system.
instead of solving for A, we're gonna solve for, sigma.
Okay,
Calculate.
so solve for sigma. So I got sigma equals K1C over Y root pi A. What's K1C? 4 megapascal root meters. What's Y?
1.
1 again. Square root of pi. And what's A?
100 micrometers, micrometers.
Or 10 to the minus 4.
How do we know what sigma is?
We're solving for sigma.
We're solving for sigma.
Right.
That's what we're trying to find. So I'm trying to find the breaking stress.
How do we know, where did the 4 megapascal?
Because that is the KIC from the
So it's
table.
given.
That's from the table. Okay?
226 megapascals.
Okay, 226 megapascal. That's the breaking stress for an ABS rod. Let's go back, just out of curiosity, and see, because I didn't do this ahead of time, if we can find from the earlier mechanical behavior chapter, if they have ABS listed in the tables there for mechanical properties. Actually, it might even be in the tables in the back,
What table?
in the front or whatever, appendices.
Which table?
I'm looking actually for miscellaneous mechanical properties of material. Here, ABS, right there. No,
What page?
nuts. It doesn't have, I was looking in the table 4, in appendix 4C. I was trying to find out if they had the yield strength for those things, for ABS, just to compare it to. Oh, there it is, table 4B, ABS. The tensile strength of ABS is between 28 and 48 megapascal. Okay? So what that says is this 100 micron defect, what does that say? Actually, I'll let you tell me. What does that say?
Multiplies this by like 5-ish.
So-
It decreases the strength. Never mind.
It's a relatively small crack.
Right, so in my graph, again,
Oh, so it doesn't
right? 226 is up here, 28 is down here. So that says, and never mind the actual scale here, what that says is my crack is subcritical. That 100 micron crack is subcritical.
So just to be clear, the sigma that you calculated for is the actual applied, not the actual additive.
Right, this is the macro.
The macro applied.
Go back to the video. It's the macro stress, or the applied stress necessary to fail the material.
To be able to get
that
a
correctly.
sigma max at the crack.
Right, so this is, I should have written an F on here. Right, to be more clear. So that sigma F is the stress at which the thing will fail due to the fracture of the material caused by a crack of length A. Does that make sense?
So at that point, it felt that much stress.
So in order for it to fail due to that crack, it would have to require 226 megapascals.
What is the graph?
But it already would have failed.
But it already would have failed because the tensile strength is 28 megapascals.
We're saying that crack didn't really affect functionality.
So we're saying that, exactly, we're saying the crack, I think that's correct, because I'm getting my, it's kind of hard to get the lines right, but I think that's correct. I think that's the same line, the ABS, right. So the point is, the ABS itself will fail before that crack causes enough stress concentration to fail it by fracture, you know, I'll pull the ABS and yield it, right, it'll plastically deform before the crack will propagate.
Oh.
Does that make sense? So it's a subcritical. This is the critical defect size, and it's a subcritical defect. So we don't care about that. So there's no point, essentially what that means is, with a piece of ABS, there's no point in polishing it to get rid of 100 micron cracks. Because those 100 micron cracks aren't changing the mechanical quality. If this were glass, I'm guessing, I didn't do the numbers, but if it was glass, we would find that that is not the case, that this is lower than the tensile strength of glass. And so 100 micron crack does matter for glass, and so you'd have to polish away 100 micron defect in glass. Good? Good. Everybody have a lovely weekend if I don't see you tomorrow.